Right. We now want to talk about weed monitoring for control measures and also predicting crop yield losses. So here we've got a field which is infested with the weeds. This is a maize crop. Now, if we focus at weed seedling emergence, normally we sample weeds when they are just emerging, and we use quadrats which we put in a field, and we make we take some counts. Individual weed species will be counted and recorded. So we go for individual weed species. Now, some of the following parameters are actually worked out or determined. Weed density. Now, weed density is important because we can relate it to crop yield loss. Weed diversity gives us a picture of the weeds which are present in that field. Sometimes it can tell us whether the weeds are actually damaging the crop or not, even if the density is there. Also, weed evenness. This can tell us whether there's dominance of certain weed species in a given environment. So if we take this data, we have a program which can easily calculate weed species richness, weed diversity, which is the Shannon-Weiner diversity index, and the weed evenness. We have got a computer program which can easily determine this. So here we have got a quadrat. I hope you are seeing that piece of wire which is in a field. So an individual has to count what is inside the quadrat, identify the plants there, and make recordings. We can also measure what is known as leaf area and the relative cover. So we can determine the leaf area of the crops and the weeds. Some of our students or colleagues, if I may call them, working in Murewa and Mutoko, they were also estimating leaf area and the relative cover using specialized equipment, and they were doing it fast because the equipment can measure this very fast. You sort of take a photograph of ground cover and it will give you the measurements. Otherwise, you may have to do it visually for relative cover. There are also GIS application techniques. We also use wheat seed banks. Soils will be sampled to a depth of 0 to 10, 10 to 20, and 20 to 30. Soils will be put in shallow trays to encourage germination, and weed seedling emergence is actually assessed. Weed seedling emergence can be taken every 2 weeks from August, September, and October. So we can estimate the weed seed bank sizes, and we can actually forecast weed infestations from this data. So I wanted to inform you that we are actually running weed seed bank studies with the soils taken from Murewa, Mutoko, across 3 ecological zones or gradients: natural region 2, 3, and 4. And we are currently monitoring the weed seedling emergence. We want to see whether different systems have got an impact on weed seed banks in the smallholder farming sector. It's a lot of work which needs a lot of time. In a field plot, this is how you can do your sampling. This is where you have those small squares. It's where you can place your quadrats. Now, if we wanted to assess the yield loss, we can use what are known as the additive experiments or studies. And the research questions will be: what is the minimum number, what is the minimum weed density which justifies weed control? What is the most competitive weed? And what is the crop yield loss? So we are also interested in the crop yield loss. We can conduct a pot experiment where we vary weed density and we maintain the crop constant. So this is how we do it. The method: weed density can be varied. You can have 0, 2, 4, 6, 8, 10, and 12 plants per pot, while the crop density is maintained constant. The treatments are replicated in an RCBD or CRD. Then you can collect data: crop height, crop biomass, leaf area, and weed biomass. But for this particular study, it is actually the crop biomass which is critical. Then we can use graphs and regression analysis to predict yield loss. Now, what we normally use are those in red. Depending on the number of your samplings, sometimes the linear regression is enough, or you may have the exponential curve, but the most commonly found model is the hyperbolic curve, the number 4-1, or even sometimes the sigmoid curve. Here we have got a statistical package known as the sigma plot, which can handle these relationships, or we can even use the ARA program to do this evaluation. So the effect of weed density on crop yield, these are some of the questions which we wanted to address. What is the weed density which justifies control of weeds in order to avoid economic yield loss? Should we monitor weed populations in cropping fields in order to plan weed control programs? Once we know the density which affects the yield, then this becomes necessary. So is the weed density the best tool for predicting crop yield loss? Or we can use leaf area. No wonder why we are also taking leaf area and cover in Mutoko and the Murewa area. Is data collected from one weed species applicable to fields with mixed weeds? This could be also one of the problems with this approach. So we've got two models. The Zimdar and the Cousins proposed the models. Now, according to Zimdar, when you vary weed density versus crop yield, at first there's a delay on the impact of weeds on the yield. But as you increase weed density, then you have a steep loss or reduction of crop yield. So what at the end, then the activity is low. What Zimdar was suggesting was that there's a certain population at the beginning, what he called low population, which is below the weed control threshold, which can actually delay the losses. Once you increase the density, then there's serious loss. Now, if we plot a crop yield loss graph using Zimdar's approach, if you look at that graph, it has got a sort of an S-shaped. It's what we call the sigmoid curve. So there are certain densities which are low, which do not cause significant losses. But as you increase weed density, you also increase crop yield loss. Then you arrive somewhere where the graph flattens. So what Zimdar was suggesting was that there's a certain density which is not necessary to control because the losses are minimal. And these are being indicated at the early part of the graph. But according to Cousins, he plotted a graph which showed loss right from the beginning. And he said that as long as there are weeds, control measures should be taken. Otherwise, there's going to be serious loss. This is what that graph is suggesting. And if we look at his yield loss graph, it showed us two areas, I, which is the slope, and A, the maximum yield loss. So as long as you have weeds, you are going to have a serious yield loss. If you want to calculate the weed control threshold using this graph, it's now a management issue. How much yield loss can you tolerate as a farm manager or as a farmer? If you say 5%, you come to the graph and work out the weed density, which you think it may not be necessary to come in with the herbicides or any other control measures. Okay, that was Cousin's crop yield loss equation, which he developed in 1985. So yield loss was equivalent to I, which is the slope, multiplied by dW, which was the density. This was divided by 1 plus, or in brackets, I again, which is the slope, and the dW, which is the density, and A this time, the maximum yield loss. So you can either use this equation or the graph to predict the crop yield loss due to weeds. However, two scientists, Croft and Spitters, thought that weed density was not very accurate in predicting crop yield loss. So they came up with the idea of using leaf area. No wonder why we're also taking leaf area in Mutoko and Mureo. So you can calculate what is known as the relative leaf area, which is a proportion of leaf area index of the weed divided by the leaf area index of the crop plus the weed. Now, if you plot a graph using LW or that proportion, you still get that it is called the rectangular hyperbola. I should have mentioned it earlier on the Cousin's graph. Now, with the relative leaf area of weeds, as you increase the relative leaf area of weeds, you also increase the crop yield loss. Our slope is now being called Q, but it's actually equivalent to I of Cousin's equation. Then A is still the maximum yield loss. In order to determine the yield loss, we multiply Q, which is the slope, times relative leaf area, which is LW. We divide it by 1, or in brackets by Q over A, minus 1, or in brackets again multiplied by relative leaf area. So that equation gives us the yield loss. But we can also just use that graph to determine the yield loss at any particular point of relative leaf area. So it is the same equation, yield loss, according to Croft and Spitters. they thought doing weed counts was not really good, and they were suggesting leaf area. Also, relative cover, which can be estimated by relative cover of the weed divided by the relative cover of the weed plus crop. So the RC, or the relative cover, can also give us the same shape if we plot it against the yield loss. I think this one is easy to use. You just go in a field and estimate the leaf area in terms of percentage of the weeds. I did this with one group of students. We found it quite accurate and less labor intensive. So it will give us the same graph which was suggested by Croft and Spitters. Instead of relative leaf area, you now have relative cover, but the equation stands the same. But it is far easier to take relative cover. I think the students or our colleagues in Murewa and Mutoko are using the instrument known as, is it the canopia, which takes relative cover easily. Again, a similar equation to determine yield loss. So it is possible to determine yield loss due to weeds in underfield conditions, and indeed we now have data which we are going to put these models into action to see what is going on in Mutoko and Mureo. What sort of yield losses are the farmers getting under natural weed infestation. Critical period for weed control is also important. Of course, we were saying density, leaf area, and so on. But the time when the weeds are present in the field relative to the age of the crop is very critical. You could have a lot of weeds which are not damaging the crop. This is another side of the story. So the question is, how long should raw weeding be delayed before there is crop yield loss? Is it 1, 2, 3, 4, 5, and 6 weeks? Or how long must a crop be free of weeds to prevent a crop yield loss? Is it 1, 2, 3, up to 8 weeks? Now, in a life cycle of a crop, there's a period when weeds do not compete with the crop, and this is key to our understanding of the impact of weeds on crops. This period is the first few days after crop emergence, and then days before the crop reaches maturity. So there are certain timelines which we should identify during the crop life cycle where the weed is not causing damage. The period when weeds compete with the crop is between 2 and 6 weeks after crop emergence. This is why we are saying our density which is critical, can actually have impact on that window. So it is important for us to identify what is known as the critical period for weed control. This can start from the time when a delay in weed control results in significant yield losses and extends to the time when weed control does not result in significant effects in increasing crop yields. And it is the period usually between 2 and 6 weeks after crop emergence. We can use these kind of treatments under field conditions if we want to assess the critical period for weed control. We can have what are known as weedy periods, or weedy period in weeks 0, there are no weeds. Then we can vary 2, 4, 6, and 8 weeks of weed competition. Then we also have another set of weed-free period in weeks 0, where you have a presence of weeds. Then we can vary the weed-free period from 2, 4, 6, and 8 weeks. And a model was created from these treatments. Now with the weedy period, if you delay your weeding, you can you can have this black line, which is decreasing as you are delaying. Then you have got the red curve, which is increasing as you are increasing the weed-free period. Now, if we have 100% of our yield right at the top there, indicated there, we say how much yield are we prepared to lose without any impact to our production. If we say 10%, it can vary depending on the manager. It could be 5%. We can mark in red there where it is 10% and draw a straight line. It starts as a dotted line. Then there's a line with arrows, 2 arrows pointing either direction. Then it ends as a dotted line again. That period is where it is harmful. If you leave weeds at that point, which we call the critical period for weed control, that is when the crop damage can occur. Even if you have the critical density of weeds, at the beginning, they don't have impact. But as you reach the critical period for weed control, you have serious losses. And also at the end, there is less damage. So as we estimate crop yield losses, we should be aware when we should actually do the assessments of crop yield loss. If we do it at the wrong time, then we get a wrong picture. So this is it on weeds.